this session on arrival and departure management. We're going to have 3 talks today. The first one is going to be given by Eri Ito. She received a PhD degree from the University of Tokyo in 2007 and currently holds a position of associate professor with Department of Aeronautics and Astronautics, the University of Tokyo. She also holds a position of chief researcher at Electronic Navigation Research Institute and National Research Institute of Maritime, Port and Aviation Technology. Her research interests cover data science, modeling and simulation in air traffic management and automation design, which support human operation, including arrival, departure, surface management, and traffic flow control. So she's going to present today a paper entitled Devising Strategies for Aircraft Arrival Processes by a Distance-Based Queuing Model. Please, Eri.
Okay, thank you very much for the introduction, and I'm going to share my screen. Can you see the screen?
Yes.
Okay, so I go. I'm Eri, and it's my great pleasure to introduce our research activities collaborating with Dresden and Singapore and Tokyo. Okay, here is the content of my presentation. First of all, I would like to explain about the research background and purposes. And then also next that I would like to introduce our model description. And then thirdly, distance-based queuing approach we employ is applied to Tokyo International Airport and the Singapore Changi Airport. And then I briefly compare the analytical results between Tokyo and the Singapore Airport aircraft arrival process. And then lastly, I'm gonna conclude this presentation and then show our future works. And then here is the introduction. First of all, as a research background, the management of aircraft arrivals at airport is central to airport operations. That's why we focus on the extended arrival management, so-called EMAN. EMAN is the system which aims to achieve efficient arrival traffic flow, covering a wider range of airspace, including terminal area and the en route area, and provides air traffic controllers with automation support for sequencing and then spacing. And this kind of system, that the EMAN system design requirements, depend on the characteristics of a given arrival air traffic flow and its surrounding air environment. For example, that the runway and airspace capacity, weather conditions, air loads, and other geometrical constraints. So we need to develop this system depending on our arrival traffic characteristics. For example, in United States from 1990s, that the traffic management advisory it's implemented in the air traffic control center, and now developing the system to en route and then terminal area, so-called time-based flow management and terminal sequencing and spacing, and the next gen program. And also in Europe, that in the SESAR project, that the enhanced EMAN, so-called kind of XMAN, targeting at Heathrow, it's developed. And in Japan, that we developed the concept, so-called multi-stage arrival management, collaborating with DLR, and then we cut each arrival stages by 4, and stage 1, 2, 3, 4, depending on the arrival traffic characteristics. And then we propose that the best efficient arrival traffic management strategy depending on each stages. In Singapore, long-range air traffic flow management, so-called LRAT-FM, is now studying. And then in this SESAR Inno Days presentation, Dr. Michael Schultz, it's our collaborators, is going to introduce the first conceptual study, I think, during this webinar. Then how, with this background, how do we design the efficient arrival traffic flow at the airport while accommodating growing number of global air traffic? As everybody knows that now we got a big impact because of the COVID-19, and then the passengers traffic is now decreasing, but depending on the JADAC, Japan Aircraft Development Corporation's research, published in March 2020, says that the demand gonna be getting back in 2 or 3 years, then now again growing. So we are facing on the 2 or 3 years delay, but this kind of forecast says that for long term that the air traffic grows. So with this background, we need to clarify these questions on how we can design efficient arrival traffic flow, considering growing number of global air traffic. So this research introduces distance-based queuing approach to aircraft arrival traffic flow at the 2 case study airports, Tokyo International Airport and then Singapore Changi Airport. And this proposing approach enables us to analyze the aircraft arrival processes at airport through queuing theory and to discuss efficient control strategies which mitigate traffic congestion while reducing arrival delay time by comparing different features of the arrival traffic flow. So now let me explain about our model description. We employ the models, so we call as distance-based queuing model. So now this figure shows the circles, concentric circles targeting Tokyo International Airport arrival traffic flow, and then this red and then blue track shows one-day track arriving at Tokyo International Airport in 2017, and then also that we draw that the concentric circles centered at Tokyo International Airport, and every 10 nautical mile until 300 nautical mile, we draw that the concentric circles. Then we partition that airspace depending on distance from the destination airport. For example, that from the center that is Tokyo International Airport, and then 10 nautical mile, and then 20 nautical mile, 30 nautical mile, and then we count this ring airspace in between 10 nautical mile circle, between 20 nautical mile radius circle, and then 20 nautical mile radius circle, 30 nautical mile radius circle. This kind of ring partitioned airspace. We have 29 partitioned airspace in this case. Using the partitioned airspace, we call it I, it's a number. Inter-arrival time and service time servers are defined. For example, that as an inter-arrival time, the time between 2 consecutive arrivals entering the airspace I, for example, that this aircraft enter this airspace I equal 1, and then after that, the next aircraft enter this circle, and this time separation we defined as inter-arrival time at airspace I equal 1. In this case, we define that the inter-arrival time for all airspace, partition 29 airspace in this definition. And then we also define the service time, the time aircraft spends flying in the airspace I. So this aircraft fly into this airspace and then go out from this ring airspace. We call it as a service time. And then we also need to define servers is the number of aircraft that are allowed to be present at any time in the given airspace I, which means the capacity of the airspace. So as an example of queuing model we draw for the partitioned airspace. So aircraft arrive, and then in the airspace I that the aircraft get services. It's the virtual servers, but we can define it as a capacity of aircraft get the service, air traffic controllers service into the in that airspace I, and then aircraft go out. So what we need to know is this stochastic distribution of the arrival time space, inter-arrival time, and the flight time in the defined airspace I, and the number of virtual servers, which means the capacity in this airspace I. Then we need to know that this kind of, okay. So we need to know the stochastic distribution to characterize each airspaces. So we use data. So we apply the data-driven analysis to get this parameter and then to make the arrival process model at the case study airport, firstly Tokyo International Airport. So we use the data, flight plans, and then track radar data for 71 days, selected all the months of 2016 and 2017. Is data we could get from the JCAB, Japan Aviation Bureau, so we use this data. And then we selected nominal operation at Tokyo International Airport, excluding the weather impact and the other rare event. And this is a character of the arrivals at Tokyo International Airport, and mainly that the arrival traffic use the 2 runways, and then 1 runway for the arrivals from southwest, and then 1 runway from the north area. So the total number of arrivals kept the maximum 40, and including 30 from southwest and 10 from the north. So we selected this 30 arrivals, congested arrival traffic from the southwest area. And then at the Tokyo International Airport, the flow control is really good. So you see that the aircraft arrivals kept really 30, number 30 during the congested period. Then we, now that based on the data, we get inter-arrival time at each airspace. So this number shows that the radii of the concentric circles. So this this data dot shows that the distribution of the inter-arrival time given from that data at the 10 nautical mile, and then we overlap the exponential distribution with this data, and you see that the aircraft is close to the airport, that there is a peak happen because the inter-arrival time it's controlled by air traffic controller, but it's getting far from that airport. It's getting really random, and then crossing to the exponential distribution. So you see this kind of characters. Then also that service time that this dot shows that data or targeting the arrivals at Tokyo International Airport, and this shows the flight time at each partitioned airspace. And for example, that this 10 to 20 nautical mile area, and then this 40 to 50 nautical mile area, that it's not so much Gaussian, but we can compare that the control characteristics given to this arrival process by using this fitted Gaussian data. So I overlap the service time, flight time at each airspace I equal 1 to 29. And then this color shows that how much far from that airport, Tokyo International Airport. So blue is really close to the airport, and then getting red that it's far from the airport. And then we see this characteristic, and then service time in between 30 to 40 nautical mile, 40 to 50 nautical mile variance is really wide because it's the entry point of the terminal area. So air traffic control gives really safety margins and then time spacing, and they are doing time spacing here. And after that, it's a kind of flow control happens under the safe operation. So, and also that aircraft speed is getting higher. So this peak is now getting converged here. And then after 200 to 300 nautical mile, that the air traffic controller gives the really best operation as user preferred. So this kind of spacing effort, metering effort, and user-oriented operation effort we can see. And then air traffic controller gives effort at each area, but it's not integrated by seeing the macroscopic view. That's what we found, this kind of data-driven analysis. Then by using these characteristics, we applied the queuing theory. And then we applied, based on this data-driven analysis, we applied two models. One is GGC model. Is a kind of arrival process, and then service time follow general distribution. And then we have multi-server system. And then waiting time, it's equal to arrival delay time at each independent airspace I. It's given from this equation. And then I don't want to explain the detail of the mathematics, but in this model that the 5 parameters decide the number of waiting time. So first of all, arrival rate, it's mean of inter-arrival time, and the second mean of service and flight time, and those variance of the service time, flight time, and the variance of inter-arrival time, and the number of servers. These 5 parameters decide the waiting time, arrival delay at each airspace I. Then in this model, the more important parameter is rho, defined by this value, and then arrival rate and mean of service time, and then C is arrival number of servers. And if this rho is getting closer to 1, the airspace is really congested. And if it's bigger than 1, this queuing system is unstable. So in order to make the stable queuing system in this airspace, that this value should be less than 1. So this is important thing. And then the other is MGC-K model we applied, and this shows arrival process follows Poisson exponential distribution, and the service time follows general distribution, and multi-server and a limited waiting room. And then in this aircraft system that we do, if the waiting room is really limited, waiting time gonna be reduced, but we cannot get aircraft back to somewhere in the reality. So we give the waiting room capacity bigger in order not to kick the arrival traffic back to somewhere. In this model, that 4 parameters decide the waiting time, arrival rate, mean of service and flight time, and number of servers, and the limited number of waiting room, this kind of thing. And then GGC model is really good to focus on the local characteristic, and MGCK model is very good for the macroscopic analysis by using this kind of arrival traffic data. Then first of all, let me explain about what is the definition of congested airspace. It means that such low values is getting 1 based on GGC model. And then this color shows that the service time, it means the flight time at the airspace I. And then here is the capacity of that the airspace I, it's a C, and the arrival rate. And then if this figure shows that these 3 parameters relations when the rho is close to 1. And then if C is bigger, and then the flight time is longer, and then this airspace is congested. And but C equals less, but the flight time in the airspace is really quick, fast, it's also congested airspace. And then arrival rate grows, then we need to process that the aircraft flying in the airspace are very quickly. This kind of characteristic this figure shows. So it's a definition of congested airspace in our queuing model. Then next, that by using this model, GGC model, and then low close to 1 congested area, we estimated maximum arrival rate we can process under stabilized air traffic. This shows that the aircraft capacity 1, 2, 3. So we increased the capacity, and then we estimated that the maximum arrival rate doable to process in the airspace I. And then now you see that when the C equals 1, that this is a maximum number of arrival rate, and C equals 2, that the arrival rate is increasing, and then C equals 3, it's really increasing. And then in order to process that the 30 arrival traffic, that the airspace I equal 1, we need capacity larger than 2. In this case, in this way that we estimated the minimum C values enable 30, 35, 40 arrival traffic in an hour. And you see that here, we need this capacity. And then currently that the Tokyo International Airport, that 30 arrivals allowed. And then in the current data, airspace I, that it's almost 2 aircraft are in. But in order to handle that arrival rate bigger, we need to increase the capacity a little bit, very close to the airport in this area. And then also that here, that when the aircraft is entering the terminal area, that the air traffic control gives really big margin, and then time spacing is given here, and then it reduces that the airspace capacity in that way. So it's also the bottleneck of reducing the maximum arrival rate in this thing. Then also that by using this model that we estimated that arrival delay time, and then here when we keep the current situation 30 arrivals per hour and the C equal to, so each airspace that the 2 aircraft are in, and when airspace between 30 to 40, 40 to 50 nautical miles, that we can estimate that this kind of arrival delay. If we keep this capacity and if we increase 36 arrivals at this part, it's really increased like this. And then, but if we increase the C capacity equals 3, then this peak values really disappears here. So it means that currently we put the 2 aircraft in the interior 10 nautical mile, it means 5 to 10 nautical mile separation. But if we can apply, for example, new separation minimum recat in this area, that the waiting time dramatically disappear, then we can handle that increasing number of arrival rate in this case. But we don't need to increase that this capacity after that 60 nautical miles, so we can do like this. Also that we did arrival strategies comparison, future arrival traffic flows, and then second, okay, sorry that I speak too much, I think. So I give the comparison that we can push back arrival delay at the further airspace. So increasing airspace close to the airport or pushing back this arrival delay to the further airspace. And then both are really effective, but increasing 20% of traffic capacity close to the terminal area, it's really efficient, but we can combine this strategy. And then now it's Changi International Airport. So we apply this method to Changi International Airport, and then we use ADS-B data, flight tracks like this. And then Changi Airport, the traffic, one-day traffic is like this. And here the Changi Airport. So we apply this data-driven approach. So I go quickly. So inter-arrival time. So that there is a characteristic inter-arrival time at Changi International Airport that at 10 nautical miles there is a peak, but after that it's really disappeared like this and getting exponential really early stage. And then also that service time is these characters. And then in order to clarify that the service time characters, we partitioned 2 arrival traffic, 1, 5, this is one group, and then 1, 2, 3, this is one group. And then the characteristic is here that the southern, from the south part, here that the service area, it's really wide variance here. And then also that this holding effect is coming here, like this. Then we apply the same approach that we estimate the maximum arrival rate at each airspace, and it's like this. So that the characteristic is here, and then okay, comparing with Tokyo International Airport, Changi Airport, that here the 10 to 20 nautical mile area, we really need to put lots of aircraft to make that queuing system really stable, because that the arrival rate is really big, and then it's coming, and then final time spacing is all happened in the current situation in this area. And then now the Tokyo International Airport here, the time spacing happened, and Changi it's here. So this is a different arrival strategy given to two case study airport. And then we have lots of results that we already estimate arrival delay time, but it's too big volume for one presentation. So I just give the summary of our preliminary results. At Tokyo International Airport, that increasing airspace capacity, reduction of separation, and introducing recat in terminal airspace and reduce variance of inter-arrival time in further airspace is the best strategy. And at Changi International Airport, use 2 runways for arrival or reduce variance of inter-arrival time and service time, especially for arrival traffic from south region. It's really important to process the bigger volume of arrival rate. And it's concluding remarks. Sorry that I speak too much. Thank you very much.
Thank you very much for this interesting presentation. Are there any questions from the audience? I don't see any now. Maybe just a very quick one that I may ask. Did you have the occasion of showing these results to representatives of the airport, and what was their feedback?
Yes, with Tokyo International JCAB, we gave this kind of result, and then I think we really need to introduce recat into the terminal area, and then the further airspace, we need to control the inter-arrival time more further than the airport. So it's going to be implemented as our system design targeting Tokyo International Airport.
Thank you. There is one question that arrived from the audience, maybe a very, very quick answer. How did you validate the results?
Sorry?
How did you validate the results in the of your experiments?
I'm not sure that I could understand this question really, but my answer gonna be really longer. So please refer my journal papers. Also, we published 3 journal papers already at targeting Tokyo International Airport. So I'm really happy you.
Okay. So what I may suggest is if you check the question and answers, then maybe you can discuss it with Dr. Mota, who proposed this question.
Okay.
Thank you very much. Yeah, sorry, I maybe should have said this before, but if you have questions throughout the presentation, feel free to type them in the question and answers part, so we will have a full vision after the presentation. I propose to go to the second presentation of our session. It's gonna be given by Ms. Hing Huo. Hing received a bachelor degree in air transportation from Nanjing University of Aeronautics and Astronautics, in China in 2015, and a double master's degree in air safety and air transportation management from the same institute, and the École nationale de l'aviation civile at Toulouse in France in 2017, and she's currently pursuing a PhD degree in the same institute in France then. Her research interest includes airport traffic optimization and optimization under uncertainty. So the paper that is going to be presented today is going to be entitled Algorithmic Efficiency Comparison of Centralized and Distributed Arrival Management Problem in Terminal Airspace.
Hello, can you hear me?
Yes, we can hear you. Hello.
Are you going to play my video? I am going to play by myself.
Yes, we are going to show the video starting.
Okay.
I will show the video immediately.
Okay, thank you so much.
I hear a very bad noise. Can someone?
Okay, so
mute?
I'll go.
Mute. Yes, thank you.
Hello everyone, I'm so glad that you're here to listen to my presentation. Today I'm going to present my work, Algorithmic Efficiency Comparison of Centralized and Distributed Arrival Management Problem in Terminal Airspace. This work has been done by me and my colleague Anige, Danielle, Philip, and Mohammed. This presentation has been divided into 5 parts. First part includes the introduction and motivation, and then I'm going to explain the mathematical model that we used in this paper. For the third part, I will introduce the adapted resolution algorithm based on our model. Then the obtained results will be demonstrated. Finally, this presentation will end with a conclusion. Let's start with the introduction and motivation. This work targets the problem in the arrival segment, as we know that arrival management is carried out by using the Arrival Manager, which is a decision support tool providing optimal arrival sequence and schedule decisions that delivers minimum delays and safety assurance. The optimal arrival sequences and times for flights are recomputed when the related information such as new arrival flight or unpredictable weather change happens. Since it is computational intensive due to the frequent update of the information, the computational efficiency for the decision support tool is really important. Based on this reason, we have proposed a new idea established based on our previous work. In the previous work, we organized the flight's information in a centralized way. That is to say, we integrated all the flight informations into each simulation during the optimization process. While, since each flight has its own decision and performance, a distributed evaluation that focuses on only one individual flight can reduce the unnecessary computational time for flights without information change. In this part, I'm going to introduce established model in our work, which includes both the centralized model and the distributed model. Our work aims to tackle the arrival sequencing and scheduling problem in a simple case. A network abstraction is proposed, and the arrival route are represented as a graph with nodes and links. Here is an example of standard arrival route in Paris Charles de Gaulle Airport for runway 26. The node set is the waypoint, and the link set is the route connecting two nodes. For the flight set, necessary information such as weak turbulence category, TMA entry node, initial required time of arrival, initial TMA entry speed are given for each flight. The decision variables in our problems are the TMA entry time and TMA entry speed. The two types of decision variable are discretized, and the deviation of the original time or speed can be selected within the designated range. For the TMA entry time, the maximum tardiness is set to be 30 minutes, and the maximum earliness is set to be 5 minutes. The time slot is 5 seconds. For the speed, the maximum available speed is 1.1 of the original speed, and the smallest speed is 0.9 of the original speed, and the speed slot is set as 0.01 times the original TMA entrance speed. Our decision vector for the flight set is also given here, includes the TMA entrance time vector and the TMA entrance speed vector. The conflict detection and resolution is incorporated in our problem. Two types of conflicts, link conflict and node conflict, are considered. For the link conflict evaluation, considering that we have two flights passing through the same link successfully as shown in the upper right figure, the conflict will be evaluated twice at the link entry point and the link exit point. Conflict will be detected if the separation between the two flights is smaller than the minimum weak turbulence separation associated with the aircraft category of these two aircraft. The minimum weak turbulence separation is shown in the table. The cost defined for the detected link conflict is 1 plus a violation percentage. This violation percentage is defined as the violation distance, which is the separation minimum minus the real separation distance between the two flights, and then divided by the minimum separation requirements. As for the node conflict detection, as shown in the figure at the bottom, a detection zone that has a radius of 2.2 nautical miles is introduced. Suppose there are two flights passing through this node successfully, and one flight is ahead of another. The node conflict is detected if more than one flight stay in the detection zone simultaneously. If a node conflict is detected, the cost of this conflict is calculated as 1 plus the violation percentage, and the violation percentage for the node conflict is defined as 2 times the violation time, which is the duration that two flights both stay in the detection zone, and then divided by the longer time that the flight passed through this detection zone. In our problem, we also consider two other interesting factors. The delay for each flight is defined as the absolute value between the assigned TM entry time and the initial TM entry time. For the speed deviation, since as a decision variable, the speed slot is set based on this initial TM entry time. Therefore, the speed deviation for each flight is calculated by using the absolute value between the assigned TM entry speed and the initial entry speed, then divided by the initial TM entry speed. The objective function of our problem takes into account the aspects that we mentioned previously. In accordance with the level of centralization, we proposed two objective functions for the centralized model that we used in our previous work and the distributed model that is proposed to improve the computational efficiency. The objective function that we need to minimize for the centralized model is simply a weighted sum of the conflicts, delay, and speed deviation for all the flights, while the objective function of the distributed model mainly focuses on the performance of individual flights. Then firstly, the cost of each flight is calculated, and then we minimize the flight with the worst performance, which is the flight with maximum cost. Since safety is always the most important issue to be addressed, that the weighting parameter for conflict should be set much bigger than the weighting parameter of delay and speed deviation. Here we set them to 1 and 0.01 respectively. Now we are going to the third part of the resolution algorithm. The resolution algorithm implemented in our problem is simulated annealing. Here I'm going to have a general explanation of how this algorithm works. The optimization process is proceeded as the temperature changes. The temperature is usually followed a geometric pattern. Each temperature is associated with an iteration. Each iteration consists of a number of transitions to ensure a sufficient exploration of the state space at this temperature. The optimization starts with an initial solution. The objective value of this solution is computed. Then a neighborhood solution is generated based on a design of this problem. The quality of the neighborhood solution and the current solution is compared. If the neighborhood solution is better than the current one, it is accepted. Otherwise, the neighborhood solution will be accepted with a probability that is specified with a metropolitan criterion. The acceptance of the worst solution explains the exception in this figure. When the transition of each temperature is finished, we move to next temperature and start with a new iteration. Then the above procedure repeats until the optimal solution is found or the minimum temperature is reached. Since the centralized and distributed almond develop different implementations for simulated annealing, the adapted algorithms are demonstrated respectively. The main difference between the centralized simulated annealing and the distributed simulated annealing lies on the neighborhood choosing and the flight simulation. In the centralized simulated annealing, the neighborhood solution is randomly choose one flight and then change one of its decision variable. The simulation for the neighborhood solution involves information of all the flight and compute the objective value. While the distributed simulated annealing is trying to focus on each flight at each transition, the neighborhood choosing is divided into two steps. Firstly, an overall simulation is conducted, and the highest cost of an individual flight among all the flights is specified. Then a threshold value for specifying the critical flights are calculated as 0.8 multiplied the highest cost. The flights that have a cost higher than the threshold value are considered as critical flights. Flights in the critical set are selected successively for each transition, and one of its decision variables is randomly changed, which will derive a neighborhood. The decision of this flight before and after the decision changing are taken as current solution and the neighborhood solution. The simulation for this neighborhood solution only involves this chosen flight and the flights that have interaction with it, and its new cost is obtained. The costs of this flight with the two solutions are then measured and accepted according to the nominal acceptance rule. After all the critical flights are optimized, this iteration is finished. The temperature is updated, then a new overall simulation for all the flights are reconducted, and the same procedures are repeated. The results obtained for both the centralized model and the distributed model. Actual arrival flights that are operated to runway 26 from a west flow configuration on 11th July 2017 in Paris Charles de Gaulle Airport are applied for our case study. This figure provides the flight information coming from 4 directions, and the mixed ratio of flights is roughly shown. In the data, we only have heavy and medium flights, and totally 437 arrival flights are operated on runway 26 at that day. The results are displayed in terms of computational time and the quality of results. Since we weight the conflict so much, as shown in the left figure, the conflicts are all reduced to 0 for the two models. While the difference is the centralized model takes nearly 16,000 transitions and the distributed model only takes 5,000 transitions, which means the distributed model can efficiently explore the state space. As the optimization process will continue, the total number of transitions are shown in the right table, in which we can see no matter the total number of iterations or the total execution times, the distributed model outperforms the centralized model. The left figure depicts the delay and speed deviations with respect to the number of transitions. Since the conflicts have the higher weight, the delay and speed deviations are mainly targeted after the elimination of the conflicts, which explain the variation trend in the figure. The results in the right table show that under the current setting of parameters, the centralized simulated annealing provides a result with less delay time and speed deviation than distributed one, where the longer execution time may help the optimization of the results. Our work can be concluded as follows. We have adapted the distributed model in the simulated annealing approach, which improves computational efficiency. Since the individual flights are targeted, the level of flexibility of the model are increased. Multi-objectives are included in our model, not only the conflicts, Other objectives can be targeted efficiently in a short time. Thus, this approach is very promising to the real application. For the perspectives, we are planning to test more complex scenarios to verify the efficiency of this model, and we want to include a larger planning horizon. And it is highly possible to seek for more opportunities to integrate the idea to other domains such as unmanned traffic management. That's all the content of this presentation, and thanks for your attention.
Thank you very much for this interesting presentation. Is there any question from the audience? Please feel free to fill the question and answers form. In the meanwhile, while we wait, I would like to ask you something that is, did you try different combination of weight in the objective function to see if they change somehow the performance of your algorithm?
Actually, for this time, no. We just tried one combination of the weighting parameters. We want just weighting more for the conflict and then weighting less for the delay and speed deviation. But I think we can try that. But and I think maybe the similar result may be achieved.
Yeah, I guess you're correct. And well, oh, we have a question that is, do you see the question and answers?
Yeah, I can see
Yeah,
the
okay. So
question.
you can.
Computer distributed system. Sorry for that because I'm not really understand what a computer distributed system is. But our model refer to the distributed is like because before we just put all the flight informations in our simulation. That means all the flight was simulated, and each time on each waypoint we will obtain that and then generate a overall simulation and have a result. But now we just focus on one flight, and every time we simulate this flight, we just simulate the trajectory of this flight and then compare with other flight who has interaction with it. That means when it have a conflict, it will have conflict just for the preceding aircraft or the succeeding aircraft. So we will choose the aircraft just near it and then simulate it. So that's how this idea is established. Sorry for that because I okay okay
We have a question. Maybe I can read it.
yeah
When you model arrivals at Charles de Gaulle, you use only runway there.
mm,
But how would you include parallel landing with runway changes in your model? That's an interesting question.
if I want actually in this model we didn't include two parallel landing runway, but if we were gonna to include it, we will choose the runway as a decision variable, and then uh, just shift the mm, as a decision variable and try to optimize the flight with the schedule and sequencing problem. I think it's similar, but just if we want to include this, we will include it as a decision variable. Only one runway.
Yeah, it was just there was a typo in the question.
Yeah, because this time we just include one runway. We just want to test it in a simple case and try to see that. But in the future, maybe we will include more complex scenario that has integrated in our perspectives.
We still have
The
a few minutes for questions, so feel free. Maybe while we wait, I may ask if you tried to tune the parameters of your simulated annealing algorithm and how you did it.
the parameter for the simulated annealing is tried empirically, because actually we have actually the parameter those parameter has indicated in the paper, but I didn't show it in the presentation. But those parameter actually we show that we just choose that empirically. If it can performs well, and we can just keep it. But actually we didn't do a lot of changes on that because normally we just use that and it performs good, and we have used it in several studies or models. um, didn't change so much, but it performs well, like the temperature, uh, the parameter for the temperature change, or the parameter for the uh, for the um, for the acceptance is just a random one. So I think it's based on your problem actually.
Thank you. We still have 6 minutes before starting the third presentation. I propose, well, we have to stick to the schedule, so if we have session jumping, it's still possible. So if you have regrets, feel free to write another question. Otherwise, I would thank you very much. It was a very interesting work you presented.
Thank you so much.
But I'm barely breathing. Just pray to a God that I don't believe in. 'Cause I got time while she got freedom. 'Cause when a heart breaks, no, it don't break even. The best days will be some of my worst. She finally met a man who's gonna put her first. While I'm wide awake, she's no trouble sleeping. 'Cause when a heart breaks, no, it don't break even, no. What am I supposed to do when the best part of me was always you? And what am I supposed to say when I'm all choked up and you're okay? I'm falling to pieces, yeah. I'm falling to pieces. They say bad things happen for a reason, but no wild words gon' stop the bleeding. 'Cause she's moved on while I'm still grieving. And when a heart breaks, no, it don't break even, oh. And what am I gonna do when the best part of me was always you? And what am I supposed to say when I'm all choked up and you're okay? I'm falling to pieces, yeah. I'm falling to pieces, yeah. I'm falling 'cause I got time while she got freedom. 'Cause when a heart breaks, no it don't break. No it don't break, no it don't break even. What am I gonna do when the best part of me goes you? What am I supposed to say when I'm all choked up that you're okay? I'm falling to pieces. I'm falling to pieces. I'm falling to pieces. Still I'm not the other one's pieces. I'm falling to pieces. Heart breaks, no it don't break even. Oh, it don't break even, no. Oh, it don't break even, no. Oh, it don't break even, no.
Hello, everybody again. In this little break, we had a new question that was proposed. Maybe you can answer a written answer there, please. And then I suggest you keep the exchanges going after the end of the session. And now I would propose to move to our third talk. It's gonna be given by Mr. Henrik Ardel. He's a former aerodynamic engineer who went on to flight procedure design, which he now combines with PhD studies. He's a first-year industrial PhD student at Linköping University and LFV. And the paper that he's going to present today is fine-grained evaluation of arrival operations. I think we have another pre-recorded video that we can start, and then we will see for the question and answers.
Hi, my name is Henrik Hadell, and I am an industrial PhD student from LFV in Sweden. I will now present the work by me and my colleagues at Linköping University, which we call fine-grained evaluation of arrival operations. Improving efficiency of arrival operations is high on the agenda of aviation policymakers both in EU through SESAR and the US through NextGen. And an objective evaluation of ATM modernization activities is possible only with a set of precise quantitative performance indicators. Such KPIs allow one to argue in favor of or against the many ongoing and envisioned initiatives, judge their effectiveness, and, if necessary, adjust their direction. ATM development goals are often set as a collection of target numbers reflecting the desire to improve various aspects of future operations, expressed in the corresponding KPI values. Most commonly, these targets are set with respect to future forecasted traffic and environment. Chasing absolute values for KPIs without taking the reality into account may be misleading, and in this work we introduce the notion of adaptive KPIs to provide the baseline for comparison of the operations against what could have been the best possible management under the given circumstances. For example, traffic demand, weather, fleet composition, environmental regulations, airspace restrictions, staffing situation, or introduction of new technologies, etc. Any KPI is affected by a multitude of factors, and by studying the effects of different factors in isolated scenarios, we will obtain a set of values, each representing the KPI when some of the factors are absent or present. Comparing the values, which we call the dimensions of the KPI, will highlight the factors which are most influential for the KPI and pinpoint where the inefficiency comes from. This work is our first attempt to develop such adaptive multidimensional KPIs for objective assessment of aircraft sequencing and to investigate the evolution of the traffic density within TMA. Our work is an adaptation of the methodology proposed by Eurocontrol EEC. Now I will describe the KPIs considered in this work and the details on how they are calculated. In general, they are defined as proposed by Eurocontrol EEC, but the calculation methods slightly differ. The first KPI we are looking at is the minimum time to final. The minimum time to final is defined as the minimum time it takes the aircraft to get from its current position to the final approach point. In order to perform the calculations, we overlay a square grid over the rectangle formed by the entry points to the TMA. We calculate the minimum time to final for each cell of the grid as the minimum time needed from any point within the cell of the grid to the final approach along any of the aircraft trajectories passing through the cell. We assign infinite or a very large value of the minimum time to final to the cells through which no trajectories pass during the considered time period. For visualization, we plot a heat map of the minimum time to final on a grid. As an example, this figure shows the actual aircraft arrival trajectories for a day with average traffic intensity, and this figure here visualizes the resulting minimum time to final for these trajectories in the corresponding grid. In this example, the minimum time to final lies between 0 and 939 seconds. Next KPI is the spacing deviation. The spacing of an arriving aircraft pair at time t is defined as the difference between the respective minimum times to final. Spacing deviation at time t is calculated for a pair of aircraft tagged as the leader and the trailer, where the leader is the aircraft that arrives at the final point first, and the trailer is the aircraft that arrives second. The spacing deviation captures the aircraft's mutual position in time and is calculated according to the formula shown here. In this formula, S is the time separation with which the aircraft pair arrives at the runway, and time is the minimum time to final. The spacing deviation reflects information about the control error, which is the accuracy of spacing around the airport. This figure shows an example of the spacing deviation calculated for 1 hour of the day with average traffic intensity. The horizontal axis shows minimum time to final of the trailer in each aircraft pair, and in this scenario the spacing deviation lies between -334 and 268. The final KPI is the sequence pressure. The sequence pressure for an aircraft at time t is the number of aircraft with the same time to final within a given time window, and it reflects the aircraft density at different time t. It is calculated for each aircraft at any time of its presence within the TMA with discrete time steps. For all our example scenarios, we chose a time window of 120 seconds. The figure here shows the sequence pressure for the same 1 hour of the day with average traffic intensity. In this scenario, the sequence pressure lies between 1 and 3, and we can observe that up to 3 aircraft intended to arrive at the same time of ±1 minute. For obtaining the aircraft flight trajectories, we use the historical database of Open Sky Networks. For this work, we have access to data representing all the aircraft arrivals to Stockholm Arlanda Airport for the year 2018. And further in the analysis, we use subsets of this data corresponding to different time periods of 2018. We found some parts of the data to be incomplete and contain erroneous records, and therefore, for efficient and reliable performance analysis, the data had to be cleaned, smoothed, and filtered. For example, some records in the dataset can show that the aircraft missed the final point, performed turnarounds, or never landed. There are also some gaps and unreasonable fluctuations in the flight trajectories, which may cause noticeable errors in our KPI calculations. We filter out all such erroneous data, leaving only the records representing complete aircraft trajectories from the time aircraft enter TMA to their landing on the runway. I will now demonstrate how to apply the proposed KPIs for the fine-grained evaluation of the arrival sequencing and spacing within TMA. The objective is to calculate the KPIs for different use case scenarios and to analyze the KPIs with respect to the different traffic situations. The different situations we chose are nighttime versus daytime operations, similar periods with different traffic intensities, periods with heavy delays, And finally, we will investigate the cases of potential separation violations for the hotspots captured by one of the KPIs. Here we have the scenario where we compare minimum time to final for daytime and nighttime operations. During daytime, there were 68 landings, and during nighttime, there were 5 landings. The figure here illustrates the flight trajectories and the corresponding minimum time to final heat maps. And from the table, we can see that there is no significant difference in the minimum time to final KPI between the daytime and the nighttime operations. Next is the corresponding spacing deviation for the same scenario, where this figure shows the spacing deviation for daytime operations, and this figure shows spacing deviation for nighttime operations. The higher traffic density during daytime when compared to nighttime operations is reflected in the higher value of the 90th quantile width in the spacing deviation KPI. The difference in total traffic volumes captured by the spacing deviation KPI is reflected in the range of the values of this KPI and in the 90th quantile width, which can easily be observed in the figures. When comparing the sequence pressure for the same scenario, we can see that for the daytime operations with 68 arrivals, we have a maximum of 2 aircraft, and for the nighttime operations with 5 arriving aircraft, we have a maximum value of 1, and this indicates that there are no signs of congestion. The busiest day of the year 2018 at Stockholm Arlanda Airport was on May 16, and the least busy day was on December 29. Here we compare the peak hours for the 2 days with the flight trajectories and the minimum time to final heat maps presented here. Comparing the flight trajectories and the minimum time to final heat maps for the corresponding peak hours, we observe that during the least busy day, aircraft are given more shortcuts. But the statistics for the minimum time to final in general do not show significant differences, as we can see from the table. The KPI for a spacing deviation clearly demonstrates that the range of the values for the peak hour for the day with high traffic is almost twice of the range compared to the low traffic day, which we can see both here in the tables and also from the figures. The width of the 90th quantile for the spacing deviation also captures that the traffic intensity is higher during the peak hour of the busiest day. The KPI for sequence pressure also demonstrates that the range of the values for the peak hour for the day with high traffic is almost twice of the range compared to the low traffic day, which we can see both here in the table and from the figures. The same observation also holds for the standard deviation, being almost twice as high for the busiest day. Heavy delays were recorded in Arlanda Airport on February 26, 2018, caused by a severe snowfall. The total of 217 aircraft arrived during that day, and according to the OpenSky data, the period with the heaviest delays was between 1 and 2 o'clock in the afternoon. The flight trajectories and the corresponding minimum time to final heat map are shown in the figure here. And here we can see that aircraft performed holding patterns and did not fly the shortest path from the entry point of the TMA to the final point for landing. And this is also reflected in the minimum time to final heat map. And by studying the statistics in the table, we also see that the maximum and average values of minimum time to final are quite high. And since severe snowfall was reported, frequent snow sweeping is required, which makes the runway unavailable for some time, and the capacity for arriving traffic reduced drastically. On this slide, we see the spacing deviation and the sequence pressure for the scenario of heavy delays at Stockholm Arlanda Airport. For example, we can see that the average value of the sequence pressure is low, which indicates that a low number of aircraft arrived during the same time window, which is also to expect during periods with bad weather when air traffic controllers might want an extra buffer and do not sequence the aircraft too tight. In addition, we studied the dynamics of the KPIs when applied to different time periods during the day with heavy delays, all including the hour with the heaviest delays. For that, we compare the statistics for all our KPIs corresponding to the 3 time periods in the table. We see that the value for the average and the standard deviation of the minimum time to final decrease with the increase of time period. The reason is that by increasing the period, we cover more and more other periods with smaller delays or not delayed at all. This obviously leads to the lower values of the minimum time to final. Then the other 2 KPIs, which calculations are based on the minimum time to final, demonstrate similar trend. The range of the values for all periods and all KPIs stays unchanged, corresponding to the extremes inherited from the hour with the heaviest delays. This use case demonstrates that the KPIs are very sensitive to the choice of the periods they are calculated for, which makes them adaptive to the actual weather and traffic conditions. An additional feature of the sequence pressure KPI is that it can be used to detect situations where potential separation violations occurred. In the scenario with the average traffic intensity, the sequence pressure of 3 was calculated between 0 and 100 seconds to final for 3 aircraft, as can be seen in the figure where the points coincide at 3. In the first case, we detected a high sequence pressure for the orange aircraft. And by searching for the position recording with the location closest to the approximate location of the final approach point, we can check at what time each aircraft passed this point. Here the separation was 80 seconds, and by applying a distance-based separation of 3 nautical miles for a medium wake vortex category aircraft followed by the medium, we conclude that the resulting ground speed to cover this distance is still realistic at this stage of flight, and hence does not indicate a separation violation problem. The second scenario with the high sequence pressure was detected for the purple aircraft. And by analyzing the corresponding data, we conclude that the purple and the blue aircraft have already landed and should not have a separation problem, and the yellow aircraft is at a safe distance and has yet time to safely land. The third scenario with a high value of sequence pressure was detected for the black aircraft. According to our calculations of time passage, we can see that the black and the cyan aircraft are separated by 106 seconds, and the gray and the black aircraft are separated by 93 seconds. Again, applying a distance-based separation requirement of 3 nautical miles, we conclude that the resulting ground speed to cover this distance is still realistic, and hence it does not indicate a separation violation problem. This work presents an analysis of arrival aircraft sequencing and spacing at Stockholm Arlanda Airport. Exploring different dimensions of the sequencing and spacing KPIs, we demonstrated on several use case examples how to perform a fine-grained comprehensive assessment of the TMA arrival performance. In addition, we showed how the sequence pressure KPI helps to capture the cases of the potential separation violations. We conclude that the enhanced KPIs can be successfully used to uncover inefficiencies in TMA, allowing the aviation authorities to pinpoint areas where efficiency is lost and suggest directions for the improvements. This work contributes to the development of the multidimensional adaptive KPIs, which will enable creating a comprehensive picture of the operations and faithfully characterizing ATM performance. Our future work will target the development of new such KPIs capturing other aspects of the TMA performance, as well as testing their applicability for evaluation of the optimization activities within TMA. Thank you for listening to the presentation of our work. I'm happy to answer any questions you might have.
Thank you very much, Henrik. It was a very interesting presentation. We have one question already in the question and answer box. Let me read it aloud for all the audience. How would you use this KPI for prediction of arrival times in TMA, and would it be a direct application or would it require more fine-grained modeling?
Yeah, I think our approach could account for that as well, and I think we have a very access to good data, and the model would be able to account for that. So I think that could be also one thing in the future to look into. Yes.
Maybe I can go for a follow-up on this question. You mentioned data, which is one of the difficult issues. How
Yes.
difficult is it to collect data for doing this quite complete and complex analysis?
Well, the data itself is readily available, and but the problems we face are the accuracy of the data, and there are errors and issues that we need to solve, and which take some time to get it ready to perform all the calculations. So I would say that that is the biggest issue for us. Yes.
And then I would like to know if you had the occasion of sharing these results with the airport, Arlanda Airport representatives.
No, not yet actually, but we are going to have a meeting with some people responsible for this kind of things in Sweden next week. So then we will share the results with them.
Brilliant. Then send somehow a a remark on what they say. We have another question. How would a performance measure look like, as the pressure indicator is a go of in situ indicator? That's what can we learn in terms of strategic decision making from aggregating such measures?
I think from this work, the key thing to bring is that we make them adaptive, and we look at them at different situations, and we can see how the KPIs behave, and then we can maybe draw some conclusions of how the operations went during the different situations. I think that is the main contribution. And then it is also important for us to apply these KPIs in our optimization work that we are conducting in our department at university. So these KPIs will provide a good baseline for us to be able to evaluate our work.
We have time, so I will keep going. When you say you are going to incorporate these KPIs in optimization, are you aiming at a multi-objective optimization approach?
Yes, we have several projects where we are using optimization in TMA. For example, where we try to schedule arriving aircraft. We start from a given realistic scenario, and then we try to optimize the arrival of traffic and still have them separated and when they are going to arrive and so on. And then to be able also to show the advantages of our optimization, then these KPIs are very handy and will give us the tools to demonstrate the advantages.
Another question, that's good. You focused on lateral efficiency. Do you foresee vertical efficiency assessment in TMA?
Not in this work. We are dealing with vertical efficiency in several other projects we're conducting, but not in this project. We did not focus on vertical efficiency. No.
For any specific reason, or just because you have to pick some?
Yeah, I think it's due to limitations. Yeah, but that could of course be one of the future work also for in this work. Yeah.
Thank you. Let's see if something else pops up. Not for the moment. So I expect this question and answer stream will be switched off with the session or with the Zoom session. So I would suggest, if you have other questions, just to use the WOVA app there. I'm sure the speakers are going to be happy to receive further comments and questions, and everybody's going to be happy to read the discussions. So thank you very much, Eric, and good luck with the following, what follows. I would like you to stay for a couple of minutes more because we have a short session, session of 4 video teasers for the poster exhibition that follows. These are for A2X, AmvirCat, SESAR 117, and virtual pilot testing. It's 1 minute for each video. I think it's worth to stay with us. Thank you very much for being here, and see you at the other sessions later.
Connected automated vehicles can already communicate efficiently with each other, but the communication between airborne and ground traffic is not standardized. These two worlds have to be brought together by a translator. That's a software able to deal with both languages, filtering out, translating, and transmitting messages relevant for the vehicles so that it will completely block all lanes of the road. These worlds have never overlapped, so bringing them together means breaking new ground.
We had our airborne drone. However, our application focuses on the helicopter.
What the police or fire brigade would do, we can now handle with the rescue helicopter.
Are you interested how remotely piloted drones will be integrated in terminal maneuvering areas and airports? Then visit us at our booth during the poster sessions. We are Project InvirCut.